All right, hello everyone. So my name is Robert, and I'll be showing you how to use deep learning on instar images. So yeah, I think if you have a question, you should just ask as we go through. It will be easier that way. So for the people in the room, I think you can use the notebooks locally. There is one, I think it's called something machine learning. For the people online, I put the link to the GitHub page in the chat, and you should try to use Google Colab for this. If you can't, or if you don't have a Google account, you can also use Binder, but it is faster on Google Colab. All right, once you open the Google Colab, change the runtime type to something that has GPU in it. That will be a lot faster. This workshop can be run on the CPU as well, but on a GPU is faster. Right. Yeah, so the purpose of the tutorial is to demonstrate how we can fine-tune a neural network that was already pre-trained, and we want to fine-tune it specifically on a data set of volcanoes, which consists of instar images. The data set contains more than 608,000 images, which for machine learning isn't that much, but because they need to be labeled for instar is quite a bit. And they are divided into two categories. So we have a few images that have deformation signal, so 3,600, and then around 3,200 without any signal in it. Originally, the network that we'll be using was trained to classify 1,000 types of natural objects, such as tables, cats, dogs. But in this tutorial, we will modify it so that it only classifies in two classes, either deformation or no deformation. Right, so well, the data set for the people in the room, you already have that, so you don't have to worry about it. If you are on Google Colab, then you need to run this, and that's gonna download the dataset, which will take 5 to 10 minutes, depending on the network speed. Right, but if you're running it in the room here, the dataset is already there, so you don't have to worry about that. Okay, so first, the imports. The main library we'll be using is PyTorch. And it is a library designed to run artificial neural networks, so deep learning. The other ones, I think you've already seen them in earlier workshops, such as NumPy, Matplotlib. The Torch Vision is also part of PyTorch, and it's specifically for images, so it's going to be useful. And sklearn in general is used for machine learning, but it can be useful for deep learning as well, because you can do a lot of pre-processing of images with it. Right. So machine learning models run a lot faster on a GPU. For this tutorial, GPU is not necessary. The use case is simple enough that you can still run it on a CPU and get reasonable times. But normally, if you actually want to train a neural network, you want to use a GPU. Also, if you're using Mac, it has MPS. So I'm running this on Google Colab, and it has a GPU, so it's going to include that. Otherwise, it's going to say CPU here. Those networks tend to be quite big, so if you have problems with memory, you can also just manually set it to CPU here, but in general you want to deploy CUDA when you run a network for real. Right, so first we need to load this data set. It contains two folders. If I can show you how it looks. So the dataset is lakes and it contains two folders, background noise and volcanic information. And each one of them has all the images from that particular type. And this is how it is expected to look like so that we can more easily load it. So those are some made dataset loaders, and they do expect this specific folder structure. You can make your own, but it's a lot slower than just using those ones. So we need to define some transformations that will be applied to the images once they are loaded. We can't just use the images as they are. Well, in this case, we actually only have one, which is just to transform to tensor. A tensor is how PyTorch stores and uses data internally. It is very similar to a NumPy array, except that tensors are specifically made to run on GPU, so are made to be accelerated on the GPU. They're also optimized for automatic differentiation, but you can think of them as NumPy in the arrays. So they store data in multiple dimensions. So it can be a 1D vector or a 2D matrix, 3D matrix, and so on. One image normally is a 3D matrix anyway, because it has width, depth, height, and number of channels, normally RGB. So each image by itself has 3 dimensions. And the only transformation we apply is just transforming into a tensor, because the images we're using here are already made to be the correct size for you. This might not be the case in other scenarios where you have to do some pre-processing yourself on the images, but here we did everything else. This specific transformation also makes the images to be from the normal interval, which is the value of pixels from 0 to 255 to just 0, 1. And in general, networks work better with images or numbers that are between either -1, 1 or 0, 1. That is because the more you use bigger numbers, the more errors you have. So you want to keep the numbers as small as possible to minimize the errors you get in when you're doing a lot of math. All right, so if we run this, it's just gonna show us the number of images we have, and then how many for each sample. Right, so background noise is gonna have the label 0 and volcanic information the label 1. And then those are how many we have from each class. Okay, so we need to split this set into training and testing. PyTorch allows us to do that at random. So if we have the number of images from each class, we can just split using PyTorch normally, but because to make sure that we have exactly the same number of images in each dataset, I'll just use a function from sklearn, the trend test split. Again, this is just so that we have exactly 2000 from each class, because otherwise PyTorch will just use all the available images. Okay, in general, there isn't a perfect way to split a dataset into training and testing, but you can use 80% for training and then 20% for testing, or 90% for training and then 10% for testing. either way, you want to have most of it in the training and then just a few images left for the testing part. Okay. Um, so the data loader is responsible for actually loading the data from your disk, in our case, the images, and it loads it into memory, both during training and testing. And we can decide how big the batch size is, so how many images we use at once. So that's the batch size option here. It also influences how good the model trains. I'll talk about that later. But essentially, a bigger batch size means better results. Um, but if you're here in the room, the resources are limited, so the amount of memory we have is limited. I was going to set this to slightly smaller numbers because, well, everyone is going to try to use them at the same time. Shuffle simply decides if we load the images randomly or not. So we will make the order random for training. For testing, it doesn't really matter. But for training, in general, if you have them at random, you can get better results, better accuracy. Because otherwise the model might just learn very specific patterns of images that because you use the exact same combination of images every time. So you want to have as much random as possible into your training. For testing, it doesn't really matter. Uh, this specific error, the one where it says put out of memory, uh, if you use machine learning, you're gonna see this quite a lot. It basically means that your batch size is too big and it doesn't fit into the GPU memory that you have. And the way to solve this is to just use a smaller batch size. Um, in general, yeah, I just have to use try a few batch sizes to see which one actually fits in the memory you have because each GPU has a different memory. Right, we can also see some of the images in the dataset. We'll just simply use the loader that we made to visualize some of them. Those are all wrapped images, and they are automatically processed from satellite. So this is just a function that shows images. And here are some examples. And we can just run this a few times to see some more. But right, so like this is what kind of information and then I mean, background noise. Right, so actually I put the theory behind deep learning here as well. Not all of this is necessary as in general you can neural networks as a black box, I guess. But you still need to know some things, which I'll point out in this slide. For the other ones, as long as you use models that are already made for pre-trained, you don't have to worry too much about it. But basically, artificial neural networks are inspired by logical neural networks that are normally called in animal brains. And it is a collection of nodes called artificial neurons, which are just an abstraction of the neurons found in the brain. So they're a lot simpler. So an artificial neuron receives signals from other neurons. So, for example, this one receives signals from all of these and then does some uh, processing on this data. It is a weighted sum, and then it has an output as well. And then the neurons in the next layer will take that output and do some more processing with it. Each of those numbers is a real number, and each neural connection here has a weight associated with it, which is really the important part because we do a weighted sum The weights are the part that we will update during training for the network. Um, the output of one neuron is computed applying a non-linear function, which in general is called the activation function. So this is the formula for one neuron, right? We have the inputs, and then each input has a weight. We do a weighted sum. We subtract some bias. Each neuron has a bias, and then we apply an activation function. In general, it's a function that looks like it's zero up to some point, and then it goes up. So it activates the neuron after a certain value. Um, Networks have an input layer, then all the hidden layers where the calculations actually happen, and then finally the output layer. The input layer in general is, well, you input your data in here, and it has the number of neurons equal to the number of real load numbers that you have in your data, and then the output layer depends on what you want to achieve. So specifically for our case, we have RGB images of size 227 by 227. Since there are RGB images, each pixel has three channels, so red, green, and blue. So in total, we have this many neurons just in the input layer. Right. So this is for one neuron, but we can write the same thing for an entire layer, where we just store all the weights of a neuron into a vector, and then all the vectors of the entire, all the weights in the entire layer into just one big matrix. And then we can calculate the output of one layer by doing a matrix multiplication between the inputs of the layer and the matrix, and subtracting the bias again, which is also a vector in this case. All right. So I will quickly go over how a network trains, but this is not that important. It is essentially this is automatically made done by us by the library that we're using. But well, if you want to know, you can learn a little bit about it. So we need an algorithm to update the weights of the network, um, such that the output we get is closer to the desired output, right? So when we first initialize the network, this is going to be very wrong, and we want to get closer to the correct output. Each input in supervised learning, which is what we do in this case, each input is paired with an output. In a classification problem, the output is a one-hot vector, which means that all the outputs should be zero apart from one, which will be one. So we have two classes, or we have background noise and then information. If an image is background noise, the output should be one in the first neuron and zero in the second. And if it's deformation, it should be the other way around, zero here and one here. The reason we use two neurons, one for each class, instead of just one neuron that has some value between, I don't know, 0 and 2, it's because we want to see how confident the network is in its decision. So we actually see the output of one neuron as the probability for that class. So we have two classes. This is how likely it is that the image is background noise, and the second neuron is how likely it is that the output is deformation. So it is a probability, which is why we need two of them. Then we need a loss function, which is just a distance function. It calculates the distance between our current output of the network and what we want, what the real output should be. And then we need to calculate the gradient of the network and then update the weights based on that. Again, this is not very necessary as it's taken care of for us. but this is important. So the weights needs to be updated using a learning rate. We cannot just use the gradient that we calculated the whole thing because the updates will be wrong. So we use some number that is small, like 0.01 or even smaller, to multiply our gradient so that when we make the updates to the weights, we actually update a lot smaller than the number we got. And I will explain why very shortly. But for now, the loss function, so the one that calculates the distance between our outputs and the correct one. Uh, First of all, it needs to have a derivative because we need to calculate the gradients. It needs to be written as a function of the output of the network, and also it should be written as an average. Most functions will be, so it's not really a problem. But the last one exists because the network is trained with multiple images at once, a batch. So we need to be able to apply the loss function to all the images separately and then get an average for that specific batch. The aim of the training is to achieve a loss value of 0, but that's not really going to happen. We can get close to 0. But the best way you would normally get close to 0 is using the entire dataset at once, each training step. So your batch will just have all the images you have, which is not going to fit into memory. In general, even like 100 images is too much to fit into memory. So we need to use smaller, a batch size of 16 or 32, something very small. But that also means that we don't calculate the real gradient. So the one calculated here is not going to be correct because we don't have the whole data set at once. We have only smaller parts. For that reason, we have to use this learning rate so that we don't overshoot. So if you think that the gradient, no, the local minimum is somewhere in here, if we use the gradient only for one batch, we can end up overshooting all the time because the average is too big, which is why we use a small learning rate so that we make small updates each time, even though we have some gradient, because it's not going to be the correct one because we haven't used the whole data set at once to calculate it. All right. So this is the algorithm. Basically, we do a number of training steps, which can be a number of epochs, for example, where one epoch is going through the entire trained dataset once. So using all the images in the trained dataset is one epoch, or we can keep going until we get a certain accuracy or until the loss function is below a certain value. Either way, we set the stopping criteria here. It's not going to stop by itself. Then this part, we just compute the output of the layers. If you use a pre-trained network, which is what we'll do today, you don't have to worry about this, because that was already done by who made the network initially. If you want to make your own network, then you need to do this part. Then the part that calculates the gradients is automatically done for us by the PyTorch library, so you don't have to worry about calculating the gradients. That is automatically done. And then, yeah, we stop based on the criteria that we made. And right, I talked about learning rate here. That is the easiest way to use the learning rate, but there are a lot more complicated ones. So yeah, I already talked about why we need a batch, because we just can't fit the whole dataset in memory. The easiest way to use a learning rate is just multiply the update with it. This is also the worst way of doing it. We will use a way better optimizer for this, but in general, you don't needs to know how they work, you can read up on how they work on either the PyTorch website or on Wikipedia or other pages. Um, but in general, this is what they do, right? They have some learning rate. It's just that they do it uh, more complicated than just having one static number. In general, they have numbers that change based on how well the training goes. Okay, any questions so far? Yep.
So what's the benefit of using artificial neural as opposed to convolution? Because we're doing image detection.
Right, yeah.
CNN works as well. Why are we using
Well, convolution neural network isn't artificial neural network. It's just that, right? So this is the easier type of method that you can define. This is a fully connected layer because all the outputs of the previous layer are used for each neuron, so it's a fully connected layer. It's the easiest one to, I guess, represent in an image. Indeed, we will use a convolutional neural network, but it's still a neural network. It's just that instead of using the output of the previous layer for each neuron, it does more complicated things specifically for images. Uh, it takes small batches of the image. That's the best way to think it. Basically, the convolutional layer, instead of because it's uh, square, the image is a square, it only takes in batches, so each neuron has a certain batch of the image rather than the whole image. But yeah, this is more for showing how a neural network looks like. We will use a convolutional one. This is just the easiest one. Yeah.
Just an interest, one of the pre-processing steps you said would be RGB image.
Yeah.
So it's so each device hardware shows you
Yeah.
you say that it's now reduced from 0 to 1.
Yeah.
By your how does I mean the network is used to achieve this would be bad information. Then if each has that we can 0 to 1, I'm just not quite sure, but I said no longer largely image. So is a rate pixel, a rate band, I think whether that works. So just thinking about how it works on multi-spectral or sort of kind of spectrum.
Yeah, no, well, in this case, it's just dividing by the biggest number you have.
Also, it's not if a rate band has like 100 like 20, it would be sound of the same value of 1 per rate. So, and the idea.
Yeah, you just want to normalize the values to this interval. So in this case, just dividing the image by 255, you get numbers between 0 and 1. So you just want to normalize all the values you have in this interval. It doesn't matter too much that they don't make sense anymore, because obviously an image between 0 and 1 doesn't show properly. But we just normalize the real values, which are between 0 and 55, by dividing by 255. And so we get those values between 0 and 1.
Or is this what do you let us using intentional application?
I say, well, I'm saying a little bit you are losing, but you're actually gaining a lot more because floating point numbers in computers, the higher the number is, the bigger the errors when you do a lot of multiplications or additions, a lot of mathematical operations in general. Uh, Normally, you don't have to worry about that if you only do a few uh, operations on a number, but with a neural network, we do thousands on each number or even tens of thousands. So if we use big numbers, by the end, we're going to have very big errors to the results, which is why we have to keep the numbers in this interval -1 to 1. So we actually lose less by doing this. Sure, you still lose a little bit when you divide and normalize data, but you get a better output because you don't have to worry about the errors that happen inside the computer, right? Any other questions? Are there any questions online? No, okay. Right. So PyTorch has a lot of pre-trained networks. Uh, in general, you can speed up your training by using a network that has already been trained. I just, well, I think someone has a question. Can you see what the question is? I think it's just. Can you ask? What do you want to know? Maybe someone had their hand raised, but I think they.
No, hand raise doesn't work, so it's just Q&A.
Right. All of those networks, they are based on, they have certain outputs and they are made for certain tasks. So in general, you have to pick one that is good for the task you're doing. Um, we are using this one here, AlexNet, because it is a network for classifying images and because it is the one that is currently running on the portal. So I think, I don't know if you saw earlier on the mechanic portal, at the very bottom, it shows, it classifies images as either deformation or not. And that's the model which runs in real time is AlexNet. So we'll just use the same one. Okay. So first we need to define the network. So in the original paper, AlexNet expects an RGB image this size, 227 by 227. That is not a problem here anymore because PyTorch uses a modified version of it. So it's actually lets you use images of almost any size. I think as long as it's bigger than 62 by 62. But because it is a modified version of the network, so it's not the original one. But in general, if you use some model from GitHub, it will have very specific requirements. So yeah, it's good to check that. But if you're just using the ones pre-trained on by PyTorch here, they are modified to work with almost any size, so that's not a problem. Right, so running this, we first download the network, and then you can actually see all the layers inside of it, and indeed it has convolutional layers. Really here is the activation function. So you see you have a convolution array, activation function, then convolution activation. This is just taking the maximum, using a kernel slice ring. This we don't have to change that. We will only change the last layer here because that is the output layer. And as you remember, the output is based on the number of classes you have. Initially, they train with 1,000 classes, things like cats, dogs, cars. We only have 2 classes, so we need to change the output layer. So this is just the last layer in the network. So it would be this one, right? The one in the output. And here we can see it's part of the classifier and it's in position 6. And we will do that in here. So because we only have 2 classes, we need to create a new layer with the output being 2. The input needs to remain the same as before because that's the input that comes from the previous layer. So the previous layer has an output of 4096, so our input needs to be the same, but the output of the layer is going to be just 2. So yeah, we modify classifier at position 6, so that's from here, right? It's called classifier and at index 6. And we create a new fully connected layer, which it is called linear in PyTorch. And then we swap the existing one with the new layer we created. They call this linear, but it is just a fully connected layer. It is might be a bit confusing at first because, well, at least they on the PyTorch website also call them fully connected layers. So you will see tutorial new fully connected and then that linear. Linear is the fully connected one. And yeah, it needs 2 numbers, the input size and the output size. Okay, the loss function and the optimizer. So yeah, I talked about loss functions, which they calculate how far our current output is from the real output. We will use cross entropy loss, which is a loss function made for classification models. So it expects an output that has a bunch of probabilities. In our case, it's only 2 probabilities. But the output of the network is not guaranteed to be numbers between 0 and 1, right? It can be any number. And also, it's not going to be exactly probabilities because the output they're not going to add together to 1. So you might get 0.7 and 0.8. Those don't add to 1. But the output is also normalized. So we can just normalize it so that it looks like proper probabilities, which sum up to 1. Well, this is the loss function used when you're doing classification tasks. If you want to read how it works, you can. Otherwise, we'll just use it as it is. But yeah, it just calculates how good your probabilities are compared to the real ones. And then the optimizer, this is the one that does the update. So it's a better use of a learning rate than the original. So it's not just one number, it actually does a more complicated update. It runs averages of both gradients and the second movement of the gradients. But its purpose is still just to update the weights slowly. So it's not the full update. It has the purpose of this, but it's more complicated than just this. Again, you can read on it if you want, but Adam is one of the most used optimizers out there. So in general, you can just use Adam. You don't have to worry too much about choosing an optimizer. It is one of the state-of-the-art optimizers. So it is going to be used in nowadays papers anyway. Not the only one, but this is one of the best ones. So in general, you can just use this without bothering to find some other optimizers. You can also leave it with the defaults. I did choose here a way to decay and learning, but you can just use it with defaults. The important part is that when you create an optimizer, you need to specify the model. so the model we created earlier, and specifically all the weights of the model, and then that's the main input of the optimizer. Right, this is so that we move the model to GPU. If you're running on GPU, if it's on CPU, it's not going to do anything. Right, so the actual training function. So we get a batch of images, and then we run that batch for the model to get an output. We use the loss function on the output, and then we call this backwards, which calculates the gradients for us, so we don't have to do that manually. And then finally, we have to call optimizer step to actually update the weights and do gradient descent. And yeah, since step is called on the optimizer that we defined, is gonna use that learning rate algorithm to update the weights. So they get updated based on the optimizer that you defined. All right, so the training function is, I'll say, the important part. So first, our topping criteria, we are just gonna train a bunch of epochs. So one epoch is when you go through the entire training dataset. You can have more complicated training stopping criteria, such as when the loss doesn't change much. So you finish a bunch of steps and you realize that your loss hasn't improved anymore, you can stop or some other criteria. But well, doing a few epochs in general is also a good way to stop. Right, so we need to set the model to training mode. There are a bunch of layers that work differently based on training and testing. So when we train, we have to set it to training. There are layers like drop inputs or layers to calculate averages for each batch. Those need to be active for training, but they need to be deactivated for training. Then we use our training loader that we defined earlier. This is gonna give us a batch of inputs and then the labels for each of those inputs. So the inputs are the images, the labels are 0 or 1, 0 being the first class, so background noise, meanwhile 1 being deformation. So this is just a vector of either 0 or 1 based on the label. We move them to the GPU like we did with the model. And then we reset the gradient on the optimizer. You can actually do this at the end, well, it doesn't matter too much, but you want to reset the gradient before you do anything. Then running it through the model is very simple. We just output the inputs and they go through the model and we get the outputs. Again, this is done for all the models that already exist in PyTorch. If you want to create your own model, then you need to basically tell it what to do in this case. But if you just use a pre-trained network like we use here, it's very simple to get the output. You just run it as if it's a function for the model. Right, so our output, it's a bunch of probabilities. We have 2 for each image, and then because we have a batch, for example, for a batch of 10, we're gonna have 20 numbers. The prediction for each class would be the highest probability. So we just take whichever one of them is the highest, and that will be our prediction as for which one is the best class. And then we apply the loss function. So again, criterion here is the loss function we define here. And it is a function that takes in our outputs of the model and then the labels. And it compares them to see how far we are from the real output. So this is the loss for this batch. which is basically a distance. And then we call backwards to calculate the gradient, again automatically done for us, and then optimize their step so that it actually updates the model. This is to get some stats for the batch. Right. And that's pretty much the training. The testing is slightly different. So we don't need to calculate the gradient for testing. But because PyTorch is optimized to calculate the gradient as fast as possible, it actually saves all the operations performed on the data, which uses a lot of memory and is unnecessary when we're testing. So we want to turn that part off so that when testing, we don't calculate any gradient. So we will just call torch no grad, which tells the library to not save the operations. All right, so in testing, we set the model to eval again because some layers work differently during training and during testing. They have different behaviors. And we call torch no grad so that we don't save any of the gradients. This part is the same, right? We use the test data loader to get inputs and labels. We run them through the model. We get the predictions, and then we calculate the loss function. But that's in testing, that is the end. We just calculate the loss, and that is it. We can also calculate the probability, the accuracy of the model, which is how many of them we got right so far. Okay, so this is the actual training. I set the number of epochs to 5 because it's enough for this. Right, I'll first run it on this, but this is on a GPU, which is a lot faster than the CPU. For the people in the room, on the CPU is going to take a bit of time, so do that as well. So we are at the same point in the program. But on a GPU, you'll see it just takes a few seconds. So it takes 12 seconds per batch, but it is on a GPU. And already after the first epoch, our accuracy is 94%. So the final accuracy is 96.5. Right, I will do this on the CPU as well so that we are at the same point because if you're running it locally on the local notebook, that's going to be on the CPU, so which is a lot slower. So on the CPU, it's going to take maybe 15 minutes. Yeah. While this finishes, any questions so far? There's some permission error. Sorry? Okay. Right, so if you run it locally here, you don't have writing permissions, so you can't modify anything. Uh, Part of the code here saves the network so that it can be loaded faster. But if you're in the room running it locally, you have to remove some lines. So this just makes a folder. This saves the current model. This also needs to be removed. Then during training, uh, here during training, we also save the best model. So also comment this. And then um, at the very end, we load the best model state that we have so far, which also won't work because you don't have writing permissions. Right, yeah, so if you're running it locally in the room, remove this part, this line, in training, this line, and then the one here.
Therefore,
Yeah, so first, the one that makes a directory here, uh, together with the function,
say,
then the torch.save. There is another torch.save here, which again just saves the current model, and at the very end, the torch.load. Right. Any other problems? Okay, my share the link. So the link is the one here on the GitHub page. It is already in here. So,
there was a question about how much processing power is bring in if you want to run it globally.
locally, um, well, first it depends if you have a GPU or not in your laptop. Um, if you have a GPU, you wanna use all the memory that it has. So you need to set up a batch size so that you use all the uh, available memory in your GPU, so all the VRAM. If you don't and you want to run it locally on just the CPU, uh, This particular example, I think it uses around 2 GB of memory, uh, RAM, and for the CPU, well, it's just gonna use all of it really. If you're running on the CPU, it's just gonna use the CPU to maximum. Uh, I wouldn't say there is a minimum because it's just gonna run slower. The slower your CPU is, the slower it's gonna run. But as long as you have enough memory, like more than 2 GB of RAM, it should run. It's just that it's gonna take a while. As you can see here, this takes 5 minutes per epoch compared to the GPU, which was around 10 seconds. Yeah, and well, if you have a GPU, it depends a lot on how much memory it has. You have to set up the batch size for that particular one. Well, someone asked, I run the model without downloading the dataset on my own computer. Does it still work? I got all the corresponding plots. Uh, no, it should not work. If you don't have the dataset, then it cannot show you any of the images. I don't know. Did you actually get the plots? Because, well, the notebook itself already has some loaded, so it has some examples already loaded. But if you don't download the dataset, it should not work. All of those images are need to be downloaded on your computer.
So 16 hits. And so what is the training loss for this?
Uh, so it's the average loss for the entire book. So we calculate the loss function for each batch. Then training loss is just the average over all the batches. Yeah, so basically it's over the entire training data set on average how big the loss was during this particular event. And the same with tests, we go through the entire test data set and we calculated the loss value and then we get the average over the test data set. You'll notice that the test is always bigger than the training because the model normally overfits on the training data, so it's gonna be very good on the training data, but it might become worse on the test data because it just memorizes the training data itself. There are ways to uh, make sure you don't overfit too much, but a little bit of overfitting is going to happen regardless. I mean, you can see actually the test loss used to be better than the training. Here it's about the same, and then here it starts to become greater than the training, and then training becomes very small. This is where we start to overfit on the training, and then the test uh, only slightly smaller than the previous event. Yeah, there are ways to try to avoid overfitting, such as layers that drop values. So basically, you put in a layer that just ignores some of the outputs of the previous layer. Um, so if you think in the layer here, you put a layer here, which will just randomly ignore some of those neurons, and then another one here, so you randomly ignore some of the other neurons. This helps with overfitting because you have to rely on a lot sparser information. So you don't just learn the training data set, you actually try to understand what's happening in the images. I don't think this one has any dropouts. There is one dropout here and another one here. Um, so it has a little bit against overfitting, but you could put more layers if you're really struggling with overfitting. This one just has two dropout layers with probability 0.5. So this means that each one of the neurons in the previous layer has a chance of 50% to be ignored. And we still have some overfitting. All right, so it finished on the CPU as well. That hopefully means that it also finished training for if you're running it locally here. All right. So we have final accuracy of 98%. The test dataset, I think, has 200 images, which means that only 4 out of 200 are wrongly classified. And we can actually visualize the predictions of the model. Um, so we get some inputs again with Torch Nograd. We run them through the model, and then the predictions are the highest probability for each of the classes. So those are the real labels, and then the predictions of the model. You can see in this case it's got them all correctly. You can run this a few times to get different images. Again, 98% means that only 4 images are wrong in 200. All right. Any questions so far? Well, this is almost the end. But if, okay. If there are no questions, that is the end of the tutorial. The reason I chose AlexNet is because this particular model is running in real time on the Comet portal. So if we go here, which is the volcanic portal, and just choose any volcano. Once this loads, and if you scroll all the way down, this is where AlexNet is run on every image. Well, so this one has nothing in it, but if we go back to run here, for this one, it found the deformation in here. This one as well. All right, so correctly identify the deformation. And you'll notice that this also identifies where exactly in the image it is. So it does a bit more than the one we trained, but really this is part of the host processing. So the network is the same, the output is the same, it's just that we use the output in a different way rather than just having either deformation or deformation. So in this case, it actually runs the model on small patches of the image. So it takes a patch and another one, and then it combines them together. Also, there are overlapping. So it's on the first this patch, one, another one, and then when it combines all of them together, So for each patch, you get either 0 or 1. You combine all of them together and get something like this. But it's exactly the same model. I think the only difference is that this was trained on MATLAB, if I remember correctly. Meanwhile, we trained on Python, but it is the same model. Yeah, and also has the graph with the probabilities. So yeah, see, yellow is 100%, and it's not so sure on the edges. And then somewhere where there is nothing, there's 0. Right. This is if you want to try an image that you have with the model we trained. So if you're in the room, I don't think you have any writing permission, so you can't load an image. But if you are on Google Colab, you can upload one image here. So you can just upload something in the folder here, and then test the model you just trained on that image. So right now, just uses some random data. This is just noise. But if you replace this with an image that you loaded, you can actually test it in the model to see what the model thinks for that specific image. And it's resized images, so you can put any resolution you want. You don't have to worry about that. It's getting resized to the correct sizes. Okay, I think that is the end. Are there any final questions? Oh, yeah. How can I download images from El Salvador, for example? I want to try the code using information from another area. Um, I think I think the workshop on time series had an example of how to download interferograms from the website, right?
Yes.
Yeah, so one of the previous workshops, the one on time series, has code for actually downloading uh, from the website. It's not in my workshop, but it's one of the previous ones. I think you can also manually download from the website, but that's slower than just using the code for that. Yeah.
This was already.
Yeah, I did answer this already. But if you have a GPU, you're fine. Otherwise, you need a little bit of RAM. This particular example uses around 2 GB of RAM, and it's always going to use like the maximum amount of your CPU or GPU. So it's going to run at 100%. It's just going to be slower if your processing power is not enough. Can we use deep learning to get an unwrapped product, especially for the rush event displacement where Snap usually fails? Please share any suggested links. Yeah, so there are actually people who are researching this. I think there was a previous student here at Leeds who was researching this, and there are some current PhD students as well looking into this, specifically training deep learning networks to do unwrapping. So yeah, it is ongoing research, and I don't think there is anything currently working. I am getting the following error while running the model. The connection to the Jupyter server could not be established. Right, so where are you running this? Is it locally or on Google Colab, or is it this binder? can we try the model with another chosen image? Yeah, so just use the final cell here to load your model, your image in here. So replace this with your image and it will run it through the model. I think the training data set has random images in it, so you can try with another volcano or another image that you have. Yeah, for this, I need to know how you're running it. In general, this error happens when you run out of memory. So if you're running this on Binder, this one, so if you use the link with Binder, this is gonna run out of memory and you need to set the batch size very small because yeah, Binder doesn't have enough resources for deep learning. It's gonna give you like 1 GB of RAM. So anything too big runs out of memory. So you have to go here and set this very low if you want to run it on Binder. It's gonna have to be something like batch size of 2. But well, I think that's the problem here. I think you're running out of Binder. Yeah. Okay. So if it is on Binder, set the batch size to 2 because Binder really doesn't have enough resources to run this with a bigger batch size. So you have to limit a lot how much memory the model needs. Right. Any questions in the room? No. I think that's not for me. Uh, there's a question.
Campus
The epoch is taking too much time to complete. Yeah, if you're running on a CPU, it's gonna take a long time. That's why in general, uh, deep learning is run on the GPU. If you're running it on CPU, especially with a very small batch size, so if you're using Binder with a batch size of 2, it's gonna take a long time. That's why I said that it's recommended to use Colab because they have GPUs and it's way faster. But on a CPU, it's gonna be very slow. There is nothing else you can do about that. That's just take a long time. Yeah. Okay.
I would agree.
Yep.
The one you have to comment.
Yeah.
Do you ever go back and check things with false positives if they improve them?
Um. Well,
Or does it improve every time, just like that?
it improved just one while. Yeah. Well, you can. Essentially, the more you try to focus on the false positives that you have, the more you're going to overfit on the training data. You can tell the model you got those wrong, do them again. But if you just focus on the ones that were wrong, you're gonna overfit on the training data set and you're gonna end up with very wrong results when you try it on the test data set. Yeah. But there are models that work like that where they run it and then they don't test it and then they run it specifically on the ones that are wrong. Um, I think the one that is on the Comet portal, it's different well. So whenever it gets a wrong one, it trains on that wrong image as well. So yeah, that is used in practice because yeah, you want to get that, but it is overfitting, but it's still used in practice. So yeah, you can do that. It's not much of a problem. You need to make sure you don't uh, destroy your accuracy on the test data. Yeah.
I guess it's one thing sort of later issues with stuff is sort of you see the these when you're running these sort of large scale, you're using things like Jasmine.
Yeah.
So you put access to Jasmine.
Yeah.
Which is something that against it's to use screens as well, access.
Yeah. Jasmine has a bunch of GPUs and they're like good ones because they are so normally when you buy a GPU, if you're just a normal person, you buy the cheap ones that are made for gaming. There are specific GPUs made for machine learning which have a lot more memory. They're also very expensive, like £10,000 per GPU. Jasmine has those GPUs, so they're like very good for machine learning. They have 40 gigabytes of virtual RAM, way higher than what you can buy as a general person. But yeah, in general, deep learning is run on big servers like Jasmine. Yeah.
Okay, so we have a program. At 3 o'clock, we have a wrap-up session. Team will also join us, have some final remarks, and also give me your certificates for in-person participants. For online participants that who attend the meetings during the last 3 days, the certificates will be sent via email. So I end this meeting and then we will start for the final remarks at 3.